Okay, so this is an example of a static equilibrium problem that involves torque. I didn't type the problem out for you, but the diagram shows there is a ladder. It has a weight of 120 newtons, and then stated here in the statement for part A, it says that there's a box of 10 kilogram, and it is placed at a distance of L over 3 up on the ladder. So that distance is measured from the floor up to where the box is, where my cursor is tracing out. So that length is L over 3. And therefore, if you can do basic math real quick, from where the box is all the way up to here, that'll be a distance of 2L over 3. And that's important to keep in mind. Okay. And the diagram also said that the wall is smooth and that the floor is smooth. So to prevent the ladder from slipping, you need to tie a string at the base there. Again, it's at the base. I just drew a little higher so you can actually see the vector later on. But you need this string, and the string is going to prevent the ladder from slipping leftward. If there's no friction, and there's no friction here, the ladder will naturally slip and move leftward, and it'll eventually flatten out. But we don't want that to happen, so we need a string to tie it to the wall here. Okay. So to do part A, to find the tension or the magnitude of the tension, I will go ahead and show you how to do this using a couple of different strategies. But it's really important that you pay attention to pivot in this case. So the strategies and the work that comes up is dictated by the pivot that you choose to when you practice these types of problems. Okay, I'll go ahead and identify all my forces given. The weight of the box is going to be 98 newtons, taking 10 kilogram times 9.8 due to gravity. The weight of the ladder is given already as 120, and everything is directed down the page in this case because the X and Y axis kept normal. The normal force exerted by the floor onto the ladder at this point of contact is perpendicular to the floor. So here's your floor, which is a horizontal, and therefore the contact force is perpendicular to the surface, which is the blue arrow. We'll call it Fn1. And then because there is a point of contact up at the very top here, the ladder is leaning into the wall. So there is a point of contact. So because the wall is vertical, the normal force must be drawn perpendicular to the surface. So since your surface is vertical, your horizontal component must be pointing to the left, in this case, in the x direction. So we'll call it Fn2. Okay. And then down here, the tension for the string just came up. In this case, the tension for the string must point to the right in order to prevent the ladder from slipping leftward and flattening out. Okay, so I have a T and question mark there because that's what A is asking us to find. So it'll keep us focused in terms of trying to figure that out. Okay, and then as I mentioned earlier, the black arrow that came up on the screen. If you can do basic math, that is a distance of 2L over 3 because from floor to box is L over 3, which means the remaining distance would be 2L over 3. All right, so here's the important stuff. I'm going to put my pivot at the very top here that runs through N2. Okay, so there's my pivot. So everything I do in this first strategy is going to be using that reference point. So because f of n2 runs through the pivot, it will generate no torque. While there is a force, you're missing a lever arm. So to do torque, you need a force and a lever arm. But as you can see, Fn runs right through this particular pivot that I've chosen. And because it does that, it generates no torque. So I'm going to go ahead and take that out of the diagram here when I set up torque. Okay. So to set up torque, we have to do counterclockwise equal to clockwise. So I'll go ahead and set this up for you. The second line comes up here. If you can visualize, keep in mind the pivot is at the wall. So if you pull the ladder to the right using the tension there, it is going to produce a counterclockwise torque. And then F of G for the box, this F of G for the box is also going to cause the system to rotate counterclockwise. So again, if you can visualize this end being stuck, and if you take the floor away, if you take this black floor away, the ladder will naturally swing to the quote unquote right, but it's going to swing in a counterclockwise direction. And the natural weight of the ladder itself, which is 120 newtons in the diagram, will also generate a counterclockwise torque. So far we have three vector that produces a counterclockwise torque. That's the weight of the ladder, the weight of the box, and then the tension, in this case, pulling the system to the right towards the wall. And then to get the system to stay still, again, you need a torque that acts in the opposite direction, which in this case is F of N1. If you, again, visualize that N being fixed, and if you take your finger and you push up on the ladder at the very bottom end of the ladder here, it's going to raise the ladder, which now causes it to rotate in a clockwise direction. Okay. All right. So now that we have your function set up, we just got to go find level arm that are perpendicular to all these forces. So watch the geometry that comes up on the screen, and hopefully the dash line will help you stay focused. Everything's color coded for you. Okay. So the first vector we'll take is t, and t is a distance of L from the pivot all the way down to the end of the ladder. That's the distance of L, but we don't want to use L. T lies in the x direction already, so we need the opposite. Uh, okay, so this dash line comes up, and that is a leg that we need because T is in the x direction. We need a level arm that goes from pivot all the way down to where T touches it visually, and where my cursor is, that's 90 degrees. So if you do basic geometry, that's going to be L sine 53 because the whole entire hypotenuse here is L, and the opposite would be, in this case, sine, due to your sine cosine definition. Okay. So, and then the next one is the weight of the box itself. The weight of the box is right there. If you take your cursor, or I'm going to take my cursor, excuse me. I'm going to go ahead and put it from pivot. I'm going to go all the way down to where this box is, and that's a distance of 2L over 3. But I need the adjacent component of that because the adjacent component in this case will be perpendicular to the weight of the box, and that's going to be 2/3 L cosine of 53. And we're almost done. And then we have a couple more here. The weight of the box is placed at the center of mass. So from cursor all the way down to f of g for the ladder, it's going to be a distance of L over 2 because this is the midpoint for center of mass. But I need this horizontal component. So if this little triangle here is the distance of L over 2, the adjacent is going to be L over 2 cosine of 53, which is what that particular green component is. And then we still have f of n down here to take care of. So we've taken care of all the counterclockwise. Again, this f of n is going to produce a clockwise torque. This f of n lies in the y direction. And from pivot all the way down to f of n1, that's the distance of L. But we don't need the y component. We need the x component because Fn already lies in the y. So this blue component that comes up is perpendicular to the normal force exerted by the floor, and therefore that particular blue component is going to be L cosine of 53. And then we just substitute all the stuff in the next line. We don't know what T is because that's what it's looking for. We know that's level arm is L sine of 53, which is this component there. Okay. And then the weight of the box, the level arm of the box, the weight of the ladder, the level arm of the ladder, f of n1, and then L cosine 53, which is drawn in the diagram. So if you're not keeping up, you might want to pause the video or go backward. Okay. L cancels out in each of these terms because it's said so mathematically. So we can go ahead and simplify everything. Sine 53 is 0.8, mass of the box is 10, G is 9.8. And then again, notice here, we already take care of the sign for acceleration due to gravity. So do not plug in a negative value for negative 9.8 here. Sometimes that's a common misconception. All the signs have already been taken care of for you in terms of negative values. And then 2 over 3 times cosine 53, that's going to give you about 0.4. The weight of the ladder is 120, L over 2 times cosine 53. So really just 1/2 times cosine 53 is 0.3. And then cosine of 53 is just 0.6. And then from here, we notice that we have a statement with two unknowns. We have t and f of n1. We're trying to solve for t. So of course, we got to go look for fn1. Otherwise, you'll be stuck with the function that has two unknowns. Okay. So we'll clean this line up a little bit here. To me, all the stuff that's in the term here, that's just a coefficient. And then 120 times 0.3, that's just coefficient. So if we add all that junk, we'll get 75.2. And then really nothing changes. So now we're stuck with Fn1. We're trying to find t. We're stuck with Fn1. So we got to set up Newton's second law. But the tricky part is knowing which direction to set it up in. In this particular case, you want to set up the y direction because the schematic that I have in the video here only has the vertical component. And the vertical component in this case would be Fn1, which is blue, which is what we're trying to find. And that lies in the y direction. So don't sit there and get confused. Do I set up sigma fx or sigma fy? I would tell you to look at the diagram and figure out what it is that you need. Fn1 lies in the y direction. So I would set up net force in the y direction. And all that junk must equal to 0 because the system is not accelerating. And then to set vectors up equals to vectors down. In this particular case, you have Fn pointing up, and then I see two vectors pointing down. Okay, the weight of the box and then the weight of the ladder. So you can just set that statement. You can just make that statement. The normal force exerted by the floor onto the ladder must equal to the weight of the box plus the weight of the ladder. Otherwise, it will accelerate up or down, which is not the case. And then here, it's just plug and chug. Fn1 is what we're trying to look for because that's what's missing on this particular statement. Using a torque, the weight of the box is 98, the weight of the ladder is 120, and then if we just simplify these two terms on the right, you get a sum of 218, and then you can substitute that into Fn1, which is over there, and this line is going to turn out to be t times 0.8 plus 75.2 equals wherever Fn is. I'm going to plug in 218, and then again everything else just carries down from the previous step. And here, you notice we're pretty much done. There's only one unknown, that's just t. So clean up a little bit by doing calculator work. 218 times 0.6 is about 130.8. And then here on the left side, the equal signs carry everything down. Combine like terms. So 130.8 minus 75.2, because that's a plus sign. Move to the right side, it changes sign. And then from here to get t by itself, we just divide both sides by 0.8. And you should get about 69.5 newtons. Okay. So that's your first strategy. The second strategy here is to shift your pivot. Previously, I put the pivot up there where it runs through the normal force against the wall, but I'm gonna actually shift that pivot here to where the tension and the normal force exerted by the floor is. So the work I'm gonna set up here is gonna be based on this pivot. So let's go ahead and draw a force out again real quick. There's the weight of the box, the weight of the ladder, yeah. F of n due to the wall on to the ladder, and that's pointing leftward. And then there's Fn1, and that's pointing up, and there's t again. We're asked to find t, but here you notice because I shifted my pivot from the wall onto the floor, f of n, okay, f of n runs through the axis of rotation, so there's no r, so I can actually go ahead and clean that up a little bit, okay, later on. But here you go. You notice here in this particular strategy, I set up sigma fx equals 0 because I know that t is pointing to the right, and in this whole entire schematic, there are only two arrows pointing in the horizontal direction. That's t pointing to the right, and that's Fn due to the wall pointing to the left. For the system to stay at rest, the magnitude of these two vectors have to stay the same. Excuse me. So I can just make the statement. I can just take the vector pointing right, subtract the vector pointing left. That must equal to 0. And if we manipulate the function, you have t is equal to Fn2, which is pretty straightforward. However, we don't know what F of N2 is, so we have to use torque. We've already set up Newton's second law of motion here, and so we're a little stuck here. But that's okay. Just set up torque, okay? But to set up torque, you have to be able to visualize what causes torque. On the screen, the blue arrow for Fn is going to disappear because it runs through the axis of rotation, so I'm going to clean that up a little bit. And in addition, you have T down here, and the pivot is there. It also runs through the axis of rotation, so I'm going to go ahead and take that away. Okay, so in this strategy, it's a little cleaner. You can take away two of your forces, Fn1 due to the floor, and also tension. So to set up torque, again, all you have to do is identify what force is causing what. So here's your pivot at the bottom of the floor. If you can visualize now taking the wall away, okay, you have to be able to visualize. If I remove this wall, the weight of the box is naturally going to cause the ladder to rotate in a clockwise direction. The weight of the ladder, it will also cause it to rotate in the clockwise directions because it's being hinged or aka pivoted right there. So both of these arrows will cause a clockwise torque, while if you pull this ladder to the direction of Fn2, it will cause it to rotate in a counterclockwise direction. So that's what I have set up here. There's only one force that creates counterclockwise. There are two forces that creates clockwise torque, and things must be equal in terms of clockwise and counterclockwise. And then we can just identify our R's. Here's F of n. It lies in the negative x direction from the pivot, which is down the floor now, all the way up to the wall. That's the length of L. And I need the component that's perpendicular to it, which is now L sine of 53. Okay, so again, here's my arrow pointing left. I need the perpendicular component of that whole entire length of the ladder, which is L sine of 53. And then here's the weight of the ladder. And the weight of the ladder is L over 2. So from pivot all the way up to the weight, that's L over 2. And then I need the adjacent component because f of g lies in the y direction. I need L over 2 cosine of 53 because that's in the x direction. And then last but not least, I have the weight of the box here in the y direction. And then from the cursor, from the pivot, the cursor is going to go up to where the box is. That is a distance of L over 3. So if you kind of visualize this right triangle right here, where my cursor is tracing back and forth, the hypotenuse is L over 3. And then we need the adjacent, which is L over 3 cosine of 53. And then from there, we just plug in math, or just plug and chuck and then just do math. Excuse me. L is going to cancel out again in the other strategy as well. And then from here, we notice on the left side here, to find t, we need to know f of n. Really, so in this case, we know everything. We have fn here as our unknown. Sine of 53 is just a number. And then cosine of 53 is just a number. 120, and then cosine of 53 is just a number. So you plug in your calculator work, you get fn is equal to 0.8. This junk reduces down to 19.66. And the green stuff here, 120 times half times cosine of 53 is about 36.1. Combine like terms, divide both side by 0.8, and you will get a answer of 69.7. Okay, I know the other answer is 69.5, but give take do a little bit to rounding error in these cosine and sine functions. All right, other than that, once we know fn2, we literally can just substitute it into the left side there using Newton's second law of motion in the x direction. So we can say that t is 69.7 because that statement is true, and that's your answer. All right, I hope that helps. I like the second strategy a little better. You just have to figure out how to do it based on your choice of pivot. But you can't go wrong with either one as long as you introduce every force and all the torque properly. Okay. All right. Other than that, don't be whack. Stay nerdy.